Let us now talk about linked list implementation of a stack in C++. So we need to create our own myStack class that supports stack operations, push, pop, isEmpty, size, and it should be using linked list internally. So this is one example use of this class. We create an instance, we insert 3 items, and this is logical view. This is how your stack would become. Internally, you would be using a linked list. This is just a logical view. Now you will be taking out, you will be printing the top item. Peek function is supposed to print the top item. We will get the top item 30. Then pop, we will remove the top item. You will get the removed item, and your stack would change this way. Now size function should give you how many items are there. Push, one more, so you will add one more item. Peek, one more, you will get the top item of the stack. IsEmpty returns a boolean value. If a stack is empty, then it's going to give you 1 or true. And if stack is not empty, then it's going to give you 0 as false. So this is one example use of this myStack class. The class should mainly support push, peek, pop, size, and isEmpty. Now please pause this video and try to implement myStack class with the help of linked list. Let us first get an idea how would you implement using linked list. So you are going to store stack items into individual nodes, that's very clear. Now how do we implement all these operations so that they can be implemented in constant time, which means time complexity of every operation should be big O of 1. See, there is one thing very clear about stack data structure, that if you are inserting at the one end, then you should also remove from the same end. Insertions and deletions should happen at the same end. Then only you can maintain the leaf order. So which end of the linked list you will pick? You will pick this end for insertion deletions, or you will pick the last end. See, if you use this end, then you would have to do some extra work, because in case of linked list, you are always given head reference or head pointer, right? In C++, you are always given head pointer. Now, if you are not maintaining the tail pointer, then to insert an item, you will have to find out the last node, then you will have to insert the new node. And if you are deleting, then you will have to find the second last node, then you will have to delete the last node, right? And even if you maintain the tail pointer for the last node, with the tail pointer, you can insert at the end in big O of 1 time, but you can't delete from the end in big O of 1 time, because you need the second last node to delete the last item. However, there is one way where we can use the last node, insert at the last, delete from the last, and maintain the tail pointer and implement all the operations in big O of 1, which is using doubly linked list. When you have a doubly linked list and you have tail pointer also maintained, then you can do all these operations in big O of 1 time. But why to do all that extra work? We can simply add an item at the head and remove an item from the head. Adding an item at the head is big O of 1. Removing an item from the head is also big O of 1. And peek is also big O of 1. You simply need to get the value at the head pointer, right? So the simple idea for linked list implementation is you insert at the head, you delete from the head. Here is linked list implementation of stack. The first thing that you will notice in this code is a node structure. This is same as linked list node. Because we are going to use a linked list, we need to have a linked list node, right? So we created a structure which has data member, next pointer, and a constructor. Now here we have our myStack structure, and we are going to use this myStack to create instances. Like we have created an instance here. Inside this structure, we have two members, head pointer and size. So head pointer is head of the linked list, and size variable is how many nodes you currently have in the myStack. So this size variable we are using to ensure that we implement size function in big O of 1 time. We are going to increment the size in the push operation and decrement the size in the pop operation. Let's now see the push operation. In push operation, we are going to insert a node at the head of the linked list. So this code simply first allocates memory for the new node that you are going to create, and we call this new node as temp. And we are going to make temp arrow next equal to head, and then head equal to temp. So this node handles all the cases, null and non-null cases. See, if head is null, even in that case, you will first allocate memory for a new node, and let's say we have initially this as temp. Let's now see the push function. Push function takes an integer value as input and creates a new node at the beginning of the linked list with this integer value. So first thing we do inside this push function is we allocate memory for a new node, and we call this new node pointer as temp. So after allocating the memory, we make temp arrow next equal to head and head equal to temp. Now, how does this work? This handles both empty and non-empty linked list cases. If head is null, then we are going to first allocate memory for 10, and we initially have this in the temp variable. Then we are going to make temp arrow next equal to head. Head was earlier null, so temp arrow next becomes null, and we are going to head equal to temp, so head becomes this. And in case of non-null, it anyways work, right? So you will create a new node, you will make its next equal to head, which was earlier 10, and then you will make this as a head, right? Temp, head equal to temp. So this becomes the head of this linked list. So this is push function, handles all the cases. Now let's see the pop function. In the pop function, we are going to remove a node from the head of the linked list. So to remove a node from the head of the linked list, we need to ensure multiple things. One thing that we need to ensure is there is no memory leak. When we are removing an item from the my stack, the memory allocated for that node should be deallocated. So we ensure that. How do we do it? We make result equal to head data, and we first store head in a temp variable, so that when we change head, we can remove temp. After doing this, we change head to next, right? So first is unlinked from the linked list, and we have hold of this temp, so we can deallocate the memory, so that there is no memory leak. Then we do size minus minus, and we return result. Result was earlier head data. So if you call pop on this linked list, first thing you will do is you will store 30 in result variable, integer variable. Then you will change head to head next. So head will come here. Then you will deallocate memory for this. And to ensure that you have hold of it, you will store it in a temp variable, right? So you will have this modified this linked list. So this is how this pop function works. See, this is a corner case in the pop function. It's underflow condition. If linked list is empty and you're calling the pop function, then you should specify that something went wrong. So to specify that, I've returned integer max. So user can check for this condition. If the returned value is int max, then I have called pop on an empty stack. You could print an error message also inside this if condition. Let's see the size function now. So size function is very simple. It simply returns the size variable. We have decremented it in pop and we have incremented it in push. Let's see the is empty function. Is empty is again simple. If head is null, then the linked list or my stack is empty. Let's now see the peek function. So peek function might also have underflow. You might call peek on an empty stack. That should be problem. So in that case, we return int max again, and in other cases, we simply return head data, because head data is the top of the link of the stack or head of the linked list. So that's how all these functions work. Here is step-by-step demonstration. Initially head is null and size is 0. That's what we do in the constructor. We first insert 10 at the beginning, then we insert 20 at the beginning, right? So because we are calling push 10, then push 20, then push 30 will insert 30 at the beginning. When you call a pop, it's going to remove beginning node, and this becomes your new head of the linked list. Now let's talk about time complexity of this implementation. You can clearly see that all these operations are big O of 1. We are not running any loop anywhere. We are just making some constant operations. So every operation of stack in this linked list implementation is big O of 1, and that too worst case big O of 1, not like vector implementation where we had amortized big O of 1.